So we just saw how we can use a 2 by 2 determinant to establish the orientation of two vectors in R2 and to calculate area in R2. What about 3 dimensions? 3 dimensions is a little bit more complicated. So the setup here is that we start with a list VWX of 3 vectors in R3. And it turns out that any list of 3 vectors in R3 falls into one of 3 categories. The first category is what's called left-hand order or negative orientation. So here's how we do this. If we were in class together, I would look at everybody and have you do this with me. So I'm just going to have to assume that you're making a fool of yourself just like I am. So here, we're going to take our left hand and we're going to make a fist. And then we're going to shoot out our index finger, and that will represent the vector v, which is the first vector in our list here. Then we'll shoot our middle finger out to point in the direction of v, but then we'll curl our middle finger into our palm like this. So like this. The middle finger now represents the second vector on the list, which is w. Now the idea is that when we pop out our thumb, if our thumb is pointing in the direction of the third vector on the list, x, that means that the orientation of the list is left-hand order, which is what we call negative orientation. So we see that summed up in this figure here. Let's look at the opposite scenario. The opposite scenario would be right-hand order, in which case the list is called positively oriented. To do this, we do the same procedure except with our right hand. Shoot out our index finger, that represents the first vector on the list v. Then curl our middle finger into our palm, that represents our second vector on the list w. And then when we pop out our thumb, we are pointing in the direction of the third vector x, that means that the list we're studying is positively oriented, which means it's in right-hand order. So 2 of the 3 categories we could be negatively oriented, which is left-hand order, or the opposite, which is positively oriented, which is right-hand order. And the third possibility is that our vectors could be not collinear, like in 2 dimensions necessarily, but coplanar, which is the analog for 3 dimensions. So this means that all 3 vectors live in the same 2-dimensional plane, which is really the same thing as saying that these 3 vectors in R3 are linearly dependent. So there's the linearly dependent category, but then if we're not linearly independent, the list of 3 vectors in R3 is either negatively oriented, which is left-hand order, or positively oriented, which is right-hand order. Again, it's absolutely crucial here that the order of the list is determined before we establish the orientation. So it's important that v is the first vector in this list, which represents the index finger. W is the second vector, which represents the middle finger. And x is the third vector on the list, which represents the thumb. Great. Okay, so how do determinants come into play here? Well, what do we use 3 vectors in R3 for? We won't use them to construct a parallelogram, but we do use them to construct what's called a parallelepiped. So this is sort of a 3-dimensional tilted cube. So let's say we use our 3 vectors, v, w, and x, to construct a parallelepiped. Well, we can put those 3 vectors, v, w, and x, into the columns of a matrix. And when we take the determinant of that matrix, the sign that we get will tell us orientation. Positive orientation means positive determinant. Negative orientation means negative determinant. And determinant equals 0 means that the vectors are linearly dependent, or coplanar. Moreover, the volume of our parallelepiped is the same thing as the absolute value of our determinant. So just like in 2 dimensions, the determinant of a 3 by 3 matrix establishes the orientation of the 3 columns of that matrix, and the absolute value of that determinant doesn't give us area, but it gives us volume in 3 dimensions. So let's see an example. Here we have an example where we are trying to figure out which of these 2 figures is correct, given are three vectors in this situation. So we have a v, we have a w, and we have an x. And we want to know which one of these two figures is depicting the correct orientation. If you stare at this for a second and play around with your hands in the privacy of your own home, you see that the figure on the left here represents positive orientation, and the figure on the right represents negative orientation. So which of these two figures is accurate given these specific numbers for v, w, and x? Well, rather than try to mess around with the coordinates and play around with my hands, I can just chuck those three vectors into the columns of a matrix and take a determinant. Here, when I take the determinant, I get the number negative 210. This immediately tells me that the list of three vectors, v, w, and x, is in negative orientation, which means my figure on the left here is incorrect. So it's the figure on the right that's accurate here, because that's the figure that depicts left-hand order. Moreover, in this example, we just calculated that the determinant of the matrix obtained by inserting our three vectors into the columns of a matrix is negative 210. That means that the volume of our parallelepiped is 210, which is the absolute value of that determinant. So we've now successfully used a 3 by 3 determinant to establish orientation and to calculate volume.